Go ahead.
Okay, so we have an exciting session with 5 contributor talks. The first one is about secure quantized training for deep learning by Marcel Keller. So Marcel, I guess you're there. Could you share your slides, please?
Yes. Or no? No, yes. Share. How is that?
It looks fantastic. Can you try to move from one slide to the other?
Tack.
Works. Super. So
Brilliant.
yeah, fantastic. So 10 minutes, take it away.
All right. Thank you and welcome to my talk. My name is Marcel Keller. I'm a researcher with CRO's Data 61 in Australia. And today I'm going to talk about secure quantized training for deep learning. And it should come as no surprise that I use secure multi-party computation for this. You already heard a good deal about MPC from Yuval. So just a quick roundup, we want to compute on secret inputs that are held by a number of parties. And conceptually, we want to replace a trusted third party by a protocol between these parties. And the model we're going to use here, I would like to call, or sometimes called black box computation, which is essentially all the parties just put their inputs into this conceptual black box, and then they have the black box compute whatever they want to compute. In this work, we're going to have 3 parties and 1 semi-honest corruption. That means that essentially every party sort of can look at their information and derive nothing from their information, but all parties are expected to follow the protocol. So that's the cryptography side. Now we go to the machine learning side. A few words about deep learning. It's an established concept in machine learning or supervised machine learning, which means that we have like known inputs, outputs. Basically, we have data where we know like what we want to figure out on some other input data. The computation is specified as a chain of functions, which are called layers. Some of these functions have parameters, and it's these parameters that we want to try to figure out during a learning or training process. There is also a function sort of quantifying the quality of the parameters, how good they work. And this function is called a loss function. And the reason to specify this loss function is that we can minimize it by basically running derivation on the loss function and with the chain rule. And this gives us a way how to update and change the parameters so that we can sort of have a walk towards minimizing the loss function. And this process is called backward propagation. All right, now going back to more crypto land, what sort of computational building blocks do we need to implement to achieve this machine learning? We went for replicated secret sharing because that allows very cheap computation, as somewhat mentioned by Yuval earlier, for fractional numbers, that is like non-integer numbers, if you will. We use quantization, or more specifically, the common fixed point representation, where you multiply the number by a power of 2 and then you just round to the nearest integer. And this implies that the addition is essentially just integer addition. For multiplication, you run the integer multiplication and then kind of have to do some sort of right shift or truncation. We use what is sometimes called the optimized dot product for linear functions, which mean that with some secret sharing schemes, you can have communication that is linear in the output of the linear function, or just basically the cost of one multiplication for a whole dot product. We implement comparisons with mixed circuits, pretty much ABY3 style. We implement division using Goldschmidt iteration. Is also an established algorithm. For exponentiation, we split the input to an integer part and a fractional part, and we use precise computation for the integer part and polynomial approximation for the fractional part. And then last but not least, in this, it turned out that we used the so-called, that is best to use an optimizer that's called AMS grad, and that relies on inverse square root, that is 1 over x squared. And we use some approximation that we also use mixed circuits for. A few words about MNIST. It has been called the hello world of machine learning. Essentially, it's a few 10,000 28 by 28 grayscale images of handwritten digits. So basically what we want to do, we want to devise a machine learning algorithm that maps these images to 0 to 9 and as correct as possible. And this is widely used in machine learning, has like some historical significance also because it demonstrated the utility of convolution, which is some sort of linear functionality that uses locality. So it looks at sort of small squares of pixels, if you will. And that already brings me to the result. We have implemented this LeNet model named after Lequin et al. This famous machine learning researcher. It uses 4 linear layers. As I've mentioned before, we use the AMS grad optimizer, which is an improvement on the better known SGD, or stochastic gradient descent. We have run our computation on 3 AWS instances, and we have found that it takes about 9 minutes per epoch, which is like one iteration of the learning process, where you go over the whole 60,000 example images in this case. And that means it takes 1 hour for 99% accuracy. So on the left side, you can see how the testing error goes down. So you run on a training set, and then there is 10,000 image test set, and you look at how correct you are on the test set. And as you can see in the graph, we are, I would say, marginally worse than running the same training algorithm in clear text. And that is probably because we use a lower precision with the fixed point quantization, and also for the sort of various mathematical functions we compute. And that brings me already to the end. There is plenty of material for this on the internet. There is the paper on arXiv. There is a specific repository for scripts and a Docker file to run this for yourself. The whole implementation is based on MP speeds, for which there is another documentation site on readthedocs.io. And last but not least, you can follow me on Twitter. And that's it. So I guess I'm gonna try to stop sharing my screen.
Thanks, Marcel. Thank you for the interesting talk. I think we have time for one little question, if there is one. Maybe just one curiosity that I just want to know. You said 9 minutes per epoch for Leonard securely. How much time would you spend on the same machine to train it, that one epoch without any security? Just to get a comparison, what the security actually costs.
Yeah, I mean, basically when you run it, it just goes like. I'm gonna say it feels like a few seconds.
Okay.
On the same one, I'm gonna say maybe 10 seconds. So yeah, to be honest, like I've run it plenty of times, but I never timed it. But yeah, okay, let's say 10 seconds.
So security costs you a factor of 60, so to speak.
Is that the math? Yeah, I guess in this context, yes. Unless I'm off and it's actually just 1 second.
Anyways, thanks again for the interesting talk. And let's, well, I think Kamit has to stop the recording.
No, for this session, we will go in a row.
Okay, all in one.
Continue.
Okay, good, fantastic. So the next talk is about ABY 2.0, which is, I suspect, the successor to ABY 3. This talk is called ABY 2.0, Improved Mixed Protocol Secure Two-Party Computation with Applications to Privacy-Preserving Machine Learning. And the talk will be given by Hossein Yalame. You already started screen sharing, so Hossein, take it away.
Hello, do you hear me?
Yes.
Okay, perfect. Hi everyone, this is Hossein. I'm here to present our paper ABY2, Improved Mixed Protocol Secure Two-Party Computation with application to PPML. This is a joint work with Arpita, Patra and Ajith Suresh from IISc Bangalore University and my advisor Thomas Schneider from TU Darmstadt. Okay, in the problem of secure two-party computation, I think all of us, we know what is the 2PC, but as a reminder, let's assume we have two parties, Yasmin and Aladdin. They have some diamonds, and the goal is to calculate number of the diamonds with the same color without revealing any information about the diamonds. And for that, we have one magic. The name of this magic is secure two-party computation. With secure two-party computation, two parties can calculate the function on private inputs without revealing any information. The state-of-the-art work for 2PC is ABY framework. In ABY, they consider 3 different protocols. I mean arithmetic sharing, Boolean sharing, and Yao-Garber circuits. They also have conversion between these protocols. And for example, in arithmetic sharing, they have chip multiplication. In Boolean sharing, they need interaction for each AND gate. And in Garber circuits, they have some communication overhead. And using conversions, they will try to use the protocols more efficiently. In high level, in ABY, we have some high level functions. And then each function should be represented as a Boolean circuits or arithmetic circuits. And then for each circuits, we can use different protocols. For example, for arithmetic circuits, we can use GMW arithmetic sharing. And for Boolean circuits, we can use Yao-Garber circuits or GMW Boolean sharing. In this work, in ABY2, we designed new arithmetic sharing, new Boolean sharing, and also we provide and designed new depth optimized Boolean circuits for all new protocols. Talking about our contribution, we have a new passively secure 2PC protocol with function-dependent preprocessing, which is not the case in ABY. In ABY, they use function-independent preprocessing, but the function-dependent preprocessing means we should know about the function we want to evaluate in advance, and is the case, for example, for PPML application, and we know the function in advance. And also we improve the online communication compared to a state-of-the-art work at least 2 times. We support multi-input multiplication at the same time. For this multi-input multiplication, we have constant online communication, And also considering this multi-input multiplication, we designed efficient building blocks. Also, we have more efficient mixed word conversions, and we designed new protocols, which is more efficient compared to ABY conversions. And especially for PPML, we have a new scalar product with online complexity independent of the vector dimension, which is the first time in the literature. The major modification of ABY2 is our new sharing scheme, which the general idea is from TDPC Astra. Let's assume we have a value V. For this value, we have two masks. The first mask is delta V in blue, and also the mask value delta V in red in the slide. The delta V in red is equal to value plus delta in blue. And then each party has these shares. Delta V in red in public, and also part of the blue value for each parties. For ABY2, addition is free, and the parties can calculate the addition locally. For that, we have X and Y, and then for X and Y can be written as a delta. And then each party has access to the share of the values of X and Y, and then they can simply adopt the shares, and then they have the share of the Z for addition. And for multiplication, again, we have X and Y, we have the share of them. And then for calculating share of Z, the parties has access to the share of X and the share of Z, I mean delta Z1 and delta Z2 here. And then similar to the traditional approach, the parties can calculate the share of mask X and mask Y. And then the parties simply can calculate delta Z1 and delta Z2, and then they can send the delta Z1 and delta Z2 together, and then they can calculate delta Z. As you can see here, for each multiplication, we need only 2 elements instead of 4 in traditional approach. Here, compared to ABY, for each multiplication or online communication is 2 elements, which is 4 for ABY. And also, as I told, we are function dependent, but ABY is function independent with the same pre-processing communication. Here we can say we are more efficient, like 2 times considering online communication. And also we extend 2 input multiplication to 3 and 4 inputs. And we can say our online communication is independent of the fanning of the gate. For example, for 4 input multiplication in ABY2, we just need 2 elements, but it is 12 in the ABY. And that's also for the first time in the literature. And also for each protocols, for arithmetic sharing, Boolean sharing, and Yalame circuit, we have the new conversion, which is more efficient than ABY. And the key highlight of our ABY2 is our new dot product. For example, for the dot product of a dimension of D, the ABY needs 4D online communication, but we need only 2 elements in online. We can say our dot product is independent of the vector dimension with the same pre-processing communication compared to ABY. Talking about our benchmarking and application, we implement ABY2 using Encrypto library, and also we benchmark over LAN and WAN with Google Cloud platform, and here we can see the PPML results. For linear regression inference, or ABY2, or runtime in ABY2 is like 6 times better than secure ML in LAN setting and 2 times in WAN setting. Also, our throughput is like 35 better than in secure ML in LAN and 11 times better than in WAN. Considering neural network inference, our runtime is better like 3 times in LAN and like 3 times in WAN. And also our throughput compared to secure ML is like 700 times better than secure ML. And the main reason of that is our new dot product in ABY2. And considering neural network training, we can see our throughput is like 3 times better than secure ML in LAN and WAN setting. And the main reason of that is our new softmax in ABY2. To conclude this talk, we can say we have new 2PC protocol for passively, securely evaluating the circuits, and we provide better mixed protocol conversion regarding RAND and online communication compared to ABY. And also we extend 2-input multiplication to n-input multiplication, but we have only 2 ring elements in online. And that's for the first time in the literature, for n-input AND gates, you just need 2 elements. And also we provide efficient building blocks, especially for PPML scalar product or a scalar product. The online communication is independent of the vector dimension. And also we have some new efficient adder, run efficient adder by combination of 2, 3, 4 input AND gates. And in a follow-up work of ABY2, we designed another building blocks like multiplication, division, ReLU operation using hardware synthesis tools. And also we have new matrix multiplication, equality test, comparison, and bit extraction, especially for PPML application. And thanks a lot for your listening, and I'm here if you have questions.
Thanks for that great talk, Hossein. While the next speaker, Deevashwer, is setting up, one quick question from Divya, who asked, is this comparison with ABY and secure ML for online complexity or total complexity?
It's for online complexity.
Okay, so for total complexity, how would the performance improvement look there?
For example, if we consider only gates, for example, here, for 4 input multiplication, for example, or setup communication is like 3 times more than ABY. But considering only online, we are very better than the ABY and especially secure ML.
Okay. There's more questions in the chat, but maybe if you can unshare your screen so the next speaker can share it.
Oh, I can unshare it. Okay, that works now, I think.
So, Deevashwer, can you share a screen now?
Yeah. Okay, can you see my screen?
Yes.
Okay.
And the next talk will be about SIRNN, math library for secure RNN inference, by a long list of authors, and Deevashwer is going to give the talk.
Okay. Hi, everyone. I'm Divashwer, and in this presentation, I'll be talking about SIRNN, which is a math library for secure RNN inference. SIRNN was published at Oakland 2021, and it is a joint work with my colleagues at Microsoft Research. So let's get started. So first of all, what is secure inference? So let's say there's a server with a machine learning model and a client with some input data, and they want to perform inference. That is, they want to learn the model output on the client's data. But this should be straightforward. However, the model is proprietary and the input data is private, so they cannot freely exchange the information. This brings us to the problem of secure inference, which seeks to answer whether these parties can perform inference without revealing anything about their inputs. This is actually possible. This is a good scenario for secure two-party computation or 2PC, which makes this kind of scenarios possible. And there are already generic solutions for 2PC, but those solutions do not lead to efficient solutions for secure inference, which is why many specialized protocols have been proposed in the past decade. So in this work, we focus on secure inference of deep neural networks, which basically have 2 types: convolutional neural networks and recurrent neural networks. So although there are many works securely evaluating realistic CNNs and like quite large CNNs have already been securely evaluated, but RNNs have been mostly neglected by the secure inference community. This is not great because RNNs are the state of the art for analyzing sequential and time series data. And they also find applications in some privacy sensitive domains like DNA sequence analysis and speech recognition. Okay, so it's clear that RNN inference is important, secure RNN inference is important, but now let's see what are the challenges in achieving this goal. So first, RNNs use floating point arithmetic, which using current techniques is not efficient. Luckily, we have automated float to fixed converters to fix this problem, which output a fixed point code, which is much more tractable with 2PC. But running this fixed point code has its own challenges. So the first one is that RNNs use math functions like exponentiation, sigmoid, tangent, and reciprocal of square root. And the existing support for these functions is inadequate. That is, it is either imprecise or inefficient. The second challenge is that the output fixed point code uses a mix of different bit widths, and prior works only support uniform bit width, which pays the cost of largest bit width everywhere. This is not great because the performance of 2PC depends critically on bit widths and degrades at least linearly with increase in bit width. So addressing both of these challenges, we have created SIRNN, which is a math library for semi-honest secure inference. SIRNN has support for mixed bit width arithmetic, which is enabled by new 2PC building blocks. SIRNN also supports math functions through our new math implementations for sigmoid, tangent, reciprocal square root, and exponentiation. And our math implementations are provably precise, which is why SIRNN suffers no loss in inference accuracy. And the performance of SIRNN is great. It is 2 orders of magnitude faster than prior work. And with SIRNN, we are the first ones to run RNN securely on speech data and perform head detection in images. In the rest of this talk, I'll mainly focus on the new mixed bit width building blocks, which have wide applicability. Then I'll briefly go over the design of our new math implementation. Then finally, I'll present the results on our largest benchmark, which performs head detection in images. Okay. So our first new building block is extension, which basically increases the bit width of the input by prepending it with zeros. The second building block is truncation, which shifts the bits of the input to the right by the shift amount. And we have 2 variants of it, logical right shift and truncated use, with the only difference being that logical right shift maintains the same bit width as the input, and truncated use reduces the bit width by the shift amount. The third building block is multiplication, which can take inputs of unequal bit widths. So using this building block, we can actually multiply a 3-bit value with a 4-bit value and output in a 6-bit value. And the final building block is digit decomposition, which takes the input and divides it into smaller bit chunks. So using this building block, we can take an 8-bit value and divide it into 4 chunks of 2 bits each. So the examples I've provided here are for unsigned operations. We also have signed variants of these operations. And in the paper, we show how to reduce signed operations to unsigned at no additional cost. Okay, now let's see how our protocols for these building blocks perform against the existing baselines in terms of communication. So for extension and digit decomposition, we are around 6 times better. For right shift and multiplication, we are up to 2 times better. And for truncated use, which is used much more often than right shift, our improvements are much larger, going up to 17.5 times. I'm focusing on communication improvements here because communication dictates the performance in our protocols as well as the baselines, as the computations are wide enough in the ML models, and the cost of rounds is thus easily amortized. Okay, so on top of the improvements I just showed, we have an additional optimization called MSP2 wrap, which makes the building blocks much cheaper if the most significant bit of the input is already known. And this is actually possible in our math implementation because we know the MSB from domain knowledge. So using this optimization, extensions become essentially free. Right shifts become almost as cheap as truncated use, and we get up to 5 times improvement for multiplication. Okay, so with these new improved building blocks, we design our new math implementations, which are inspired by embedded systems, in that they use lookup tables to avoid complex computations, and they use low bit width fixed point arithmetic, which is great for 2PC because of its low bit width. And we design new implementations for exponentiation, sigmoid, tangent, and reciprocal of square root, which have been carefully designed to ensure minimal bit widths, and they also use mixed bit widths. And as alluded to earlier, we use domain knowledge in all our math implementation to determine MSB of all the intermediates, which is why the MSB to tab optimization from before is applicable. And we can use cheaper mixed bitwidth building blocks here in all the implementations. Our implementations are verified for correctness through exhaustive enumeration, which is possible for small bitwidths like less than equal to 32, which are used in ML. And our functionalities, like we proved that our functionalities have less than 4 elf error, which means that the output is contaminated in at most 2 bits. Okay. Putting all these components together, we implemented our math library SIRNN, which takes just 16 microseconds per sigmoid operation. In comparison, prior work is either imprecise or inefficient. For example, Minion used a 12-piece spline in all of their benchmarks, and which has large elf error. If we were to take Minion strategy and make its precision comparable to SIRNN, we would require 48 pieces, which would make it 115 times slower. The other 2 baselines of deep, secure, and MP speeds are also at least 80 times slower. Thus, SIRNN is precise as well as 80 to 115 times faster than prior work. Okay, so the largest benchmark we evaluate is the heads benchmark, which is a state-of-the-art network combining CNNs and RNNs. The job of this network is to identify human heads in an image. And this huge network contains 136 sigmoid and tanh layers each, and a total of 3 million calls of 3 million calls to both sigmoid and tanh. And like this number is actually 3 orders of magnitude larger than the number of sigmoid and tanh instances considered by any of the prior works. And this network also has L2 normalization layers, which use reciprocal of square root. And so in evaluating this network, half of the time is spent in performing sigmoid and tanh, which despite our large improvements. So this shows that how important it was to make these operations efficient. And to finally to evaluate this network using SIRNN, we just take 7 minutes and 85.5 GB of communication. And these are total communication and total time. In conclusion, we've created a new math library for secure inference, which is 2 orders of magnitude faster than prior work. Our math library SIRNN has support for mixed bitwidth arithmetic, and it also has efficient and provably precise math implementations. Our code and paper are public, and I highly recommend that you check them out. And that's it. Thank you for your attention.
Thank you for the great talk, Deevashwer. Yeah, I think maybe if somebody has a question, please go ahead with it. Otherwise, thank you again. Let's move on to the next speaker. I have one question. What is the round complexity of the math functions?
The round complexity of the math functions would be, so it's comparable to, so it's definitely more than, let's say like Minion, which uses a purely Gabler circuit based approach. So that would be 2 rounds, but the other comparison was with MP speed. So I would say it's comparable to that. So it's comparable to all the iterative approaches where you take an initial approximation and then you iterate over it using multiplications. So it would be, yeah, so it's comparable with all those approaches.
Okay, I hope that answers your question, Amit. The next speaker would be Sherman Chow. Sherman, if you can share your screen. And Sherman is, hello, Sherman is going to talk about differential privacy for text analytics via natural text sanitization. So Sherman, take it away.
Thank you. So hi everyone, I'm Sherman Chow from COHK. Okay, so let's just get way started. So we see a recent great progress in general purpose language model or LM, such as GPT or BERT BERT from Google. Meanwhile, as you can see on the screen already, we have found some privacy concern. So in particular, let me highlight one attack, which basically the same old stuff. Given the language model, you can extract the sanitized data. Sorry, it already advanced to this one. And okay, so so today's focus will be we want to ensure text privacy, and our approach will be text sanitization. And we try to say we produce sanitized tests to preserve privacy from the roots, which we will make myself clear in the next slides. We consider this as from two aspects. One is about test representation. And for this population, I guess I don't need to motivate too much about the need of a special approach because, for example, the simple approach of removing PII won't work due to sophisticated re-identification attack. Okay, and now, so let me quickly talk about some prior work. And actually, as a matter of fact, we don't have too many related work from the literature. We try to broadly classify them into two main categories. So the first one that also addressed the question I left in last slide is one existing approach will be to produce sanitized tests via noisy token embedding. So what do I mean by that? So let's say we have a token or vocabulary called like bank. The workflow first get is embedding vector from some embedding model such as graph. Then with that vector we add Laplacian noise over it. We got a noisy embedding, and that is the last stage which we find a bit problematic. Given the noisy embedding, the approach will be trying to do a nearest neighbor search over the entire vocabulary to map it back to the vocabulary, and in this case, maybe it back to auto-teller machine. So in this process, we find that there is two large noise involved, which lead to the curse of high dimensionality, and because of the NN search, it's also not that efficient. There are also specialized approach, for example, the one from SIR 2018, which specifically focus on term frequency vector. But yes, the problem is it just takes care of one kind of test analytics instead of like general tests. So that is one aspect why we say we try to address the problem from the roots. And so here is our problem statement. So as you might expect, we are trying to propose a differentially private mechanism. There is a token level mechanism which try to preserve the semantic meaning of the token. And that we just don't stop there. The next step of our approach is, given we have this kind of DP sanitization mechanism, can we do more about that? Can we address the whole pipeline of the test analytics? So that is what I meant by address the problem from the roots from the second perspective. So we try to use our mechanism to also benefit or adapt the existing popular pre-training fine-tuning paradigms such as BERT on standardized tests for downstream tasks, which I will make myself clear in a few slides. So as the first contributor talk, and maybe the only one which focus on local DP, so I found the need to have this slides. So to quickly recap, that is a mechanism that has been deployed in many settings. Local aspect means that each of the user or the data contributor add some noise to their data, send the noisy data to the analyst do some analytics task over the noisy data set contributed by a different one. So that is local DP mechanism in a nutshell. And the privacy guarantee is captured by this inequality, and we have this epsilon as the parameter, tunable parameter for the privacy budget. So that is like the trade-off between privacy and utility. We will use two LDP variants. Oops, I'm sorry about that. So one existing variant which was proposed in CSF is matrix LDP. So as you can see on the screen, instead of considering a uniform privacy budget, it sort of adapt to the distance according to certain matrix of two items to be sanitized. So if the two items are far, then that naturally there cannot be too many privacy. If something, that's the intuition. That's the first variant we consider. And the second one is so-called utility optimized LDP, which is recently proposed in user security 2 years ago. In a nutshell, we try to allocate our budget wisely. So there can be some token which is non-sensitive, and for those non-sensitive token, we may apply the LDP mechanism, and we may not. And obviously, if we try not to apply LDP for all non-sensitive token, there will be a problem. So that's also why in this case we flip a con. So in this case, yes, as mentioned, the privacy budget can be spent wisely to protect the really privacy sensitive data. So in this work, Sorry, my keyboard must have some problem. So in this work, we propose two mechanisms. The first baseline SIRNN test just use matrix LDP, and the mechanism is we try to sample a token Y with probability inversely proportional to the distance over the embedded encoding of the vocabulary. So in this case, we capture also the distance matrix. So there is a toy example. So bank may be sort of similar to ATM, but it may be too different from other vocabulary, say chair. So that is how we sample the token, and we sort of sample it directly, so it circumvents the curse of dimensionality instead of the art. And the next one is SIRNN test plus our main mechanism, which also incorporate the utility optimized LDP notion. So we divide the vocabulary space into sensitive and non-sensitive part. And in particular, for our experiment, we just use a simple approach of taking popular work in a certain vocabulary that we consider it to be non-sensitive, such as like AND or others very common vocabulary. So of course we can use more sophisticated mechanism, but in our experiment this suffice. So again, as a toy example, maybe we are considering financial statements. So Hannah, the lamb, and the amounts will be sensitive, but withdrawal deposit is like a regular operation, so we don't consider to be sensitive, and then we add the noise accordingly. Okay, so let's quickly overview our mechanism. And now the second part of the work. So now we have a mechanism, so we try to make the whole process or the whole pipeline more sanitization aware. So what do I mean by that? So firstly, that is from the language model, we have pre-training and fine-tuning, and we also apply SIRNN test plus over the raw public corpus to get a standardized public corpus. And obviously the reason for here is not for privacy, because the corpus is out there anyways. The reason is we sort of want to get a language model which is like get used to our standardized test. So in a little bit more detail, in the language model, they work by masking a certain token and try to use the rest of the document, which obviously give you the semantic context to predict the original token. So that is a rough overview. And for the next stage of fine-tuning, we have two approaches. So you can either just fit in the standardized test to the regular model or our standardization aware language model. Okay, and for the interest of time, I just highlight two experimental results. So we try to use the some standard data benchmarking data from the NLP community, and then you can basically see the conclusion here is if we try to use accuracy as the utility, then yes, we just have a reasonably good enough accuracy and a great improvement over the prior art. So that's one aspect. And the next one is about our major concern, privacy. So we try to use the language model prediction mechanism to sort of attack our own model. That is a very rough description of the attack. And as you may expect, so the idea or the results here is that somehow we can improve the defense rate according to the definition you can see on the screen with only a small accuracy loss. So to me, that is like the interesting part, because it's sort of exhibits some kind of crypto behavior. It is preserving the semantic meaning for the good guys, but it does not really boost up the attacker's successful rate. So we also did more experiment in the paper, so feel free to check it out. And then for here, I spent 10 seconds to quickly advertise some of the other work from our group. Okay, so to summarize, so that is our DP sanitization approach, and thanks to the first two authors, and they did some great work in formulating the problem and also make the code available. So for here, I also quickly highlight two questions. So with that, thank you for your attention. I'm ready to take your questions or comments.
Thank you for the talk, Sherman. I think in the interest of time, if there are questions, could you please answer them then in the chat? That'd be helpful, or ask them in the chat.
Thank you so much.
For the last speaker of the session, that is Moran Baruch. Moran, could you please share your slides?
Just a second.
Moran.
Sorry, doesn't let me to. Sorry. Privacy restrictions. I'll try again.
Yes.
Okay. Just a second. Can you see it now, or I need to close and open again?
Still don't see anything.
Okay. The line's going to work. You see it now?
Okay, now we have it. So,
Sorry.
good. Moran is going to talk about fighting COVID-19 in the dark. So, yeah, please go ahead with the last talk for the session.
Hello, my name is Moran Baruch from Berlin University and from IBM Research Lab. This is a joint work with Levenberg and Guy Moshkovitz, and today I'm going to do about fighting COVID-19 in the dark, methodology for improving the inference of homomorphically encrypted deep neural networks. So our motivation is to run deep neural networks in untrusted cloud environments in a non-interactive manner. It's crucial for many domains, and we will specifically talk about COVID-19 datasets. So here we have two datasets, one for chest CT and the second for chest X-ray. And our goal is to classify these images to one of three cases: normal, pneumonia, or COVID-19. So one way to use it is with fully homomorphic encryption, which is a form of encryption that enables computation of arithmetic operations over encrypted data without decrypting it. However, each arithmetic operation adds an accumulated noise, and after a maximal value of allowed multiplication, the ciphertext cannot be decrypted anymore. So there is a solution called bootstrapping that removes the accumulated noise, but it costs in slow runtime. We focus on one FHE scheme, which is called CKKS. We chose it because it's the fastest scheme that allows homomorphic addition and multiplication over real numbers, which are mostly needed for deep learning inference. So our goal is to define a set of methods for training an efficient CKKS compatible model for secure inference. However, it's not an easy task since common deep learning architectures use non-polynomial operations. For example, in the right, you can see the AlexNet architecture, which is a network for image classification. It's a convolutional neural network with convolutional layers. Can you see my mouse?
Yes.
Okay, so there's a convolutional layer, pooling layers, and fully connected. Also on the output, we use the softmax, and we have ReLU activations. So this, there are some, the max pooling, softmax, and non-polynomial activations are not supported by the CKKS scheme. So previous work have quite good solutions for the max pooling, softmax. Since the max operation is not allowed, it's like an if condition. We use average pooling instead, and it works quite well. And also for the softmax, which works on the output layer, it uses exponentials, and we cannot use it for CKKS. So since it works only on the output, we send to the client the logits, and the client in turn decrypts it and performs the softmax by themselves. So, but we still have the activation function issue. The standard activation function that we saw in AlexNet, for example, is called ReLU, which is defined as the maximal value between X and 0. But as we said before, we cannot have max in CKKS scheme. So we stick for a polynomial alternative. And the most common approaches that were used in the previous works are the square activation and the ReLU polynomial approximation. But as you can see in the bottom left, in the range between -1 to 1, the orange line is the ReLU activation. The green is the square activation, which only on the positive side approximating the ReLU activation, and the blue line is the ReLU approximation, which looks like a linear line. So if we zoom out, we see that the square activation totally explodes, and the approximated ReLU looks quite good. But if we zoom out more to a larger range, both activations explode. So we would like to show techniques to improve the performance of the models with the new activations over real data sets to improve convergence and avoid accuracy degradation. The first method I'm going to show is called the trainable activation function. So instead of using fixed coefficients that will not support different ranges of values, we would like to let the network choose the right activation. I forgot to mention that, as we said before, that we are limited in the number of multiplications. We would like to use only polynomial of a second degree to avoid bootstrapping. So here we have an activation, a polynomial, activation of second degree. And we would like to set to let the network choose the right A and B coefficients for each activation layer separately. So the network will know to choose which scaling works the best for each layer and for each dataset. And all the training, during the training of the network with the entire weights, it will also train the activation function. So here we can see the previous works with on the chest CT and chest X-ray datasets with the square activation and approximated ReLU. The bottom line is the reference network with ReLU and max pooling. And we see that the trainable polynomial performs the best, but still there is a gap to the ReLU activation. So now I'm going to talk about how to change the activation, which we call it the smooth transition. If you remember, we used the original model needs the ReLU activation, but when we move to a polynomial of a second degree, we change all the activation to a polynomial of a second degree, it can shock the network and degrade the performance. So we would like to avoid that by gradually replacing each activation. For example, here we have the weighted activation. We chose a round of 10 epochs. We would like to change gradually for 10 epochs. For example, we start with ReLU activation and gradually shift to the trainable polynomial until we have only a trainable polynomial activation. And we can see here before the smooth transition and after the smooth transition that we perform better now. So we will move to our last technique, which is called knowledge distillation. We adopted a known technique where knowledge distillation is used in a deep neural network to train a small model out of a big large model which is pre-trained. So the large model is called the teacher model, and the small model is called the student model. This is pre-trained model, and for example, if we have images, when we want to train the student, we feed both of the models with the training data, and we take the soft labels, the output layer, the output of both networks, and we would like to minimize the distance between both outputs. In our case, for HE, we don't want to reduce the number of layers, but we would like to use as a teacher the model with the prohibited activations. So the teacher model will be the original network with max pooling and with ReLU, and the student model will be the one with the trainable activation and average pooling, and the teacher model will let the student model to learn how to choose the right coefficients and the other weights as well. And we see here that now with the polynomial, with knowledge distillation, we are only between 1 to 3% away from the reference with ReLU. So to summarize, we show here the full table, and we see here that with our methodology, we improved the performance of the model and closed the gap significantly comparing to previous models. Question?
Thank you for the nice talk, Moran. So for questions, I think they should probably be either in the Zoom chat, or there's also a Zulip chat for this workshop on the ICR website available. I think that'd be the end of the session. Thanks again to all of the speakers. And if I see that correctly, then we will